Okay, so let's start. Last time we did calculations about calculations for the stresses when we know the stress resultants. So we represented sigma 1 in terms of N1, M2, and M3. So all these are sectional stress resultants. N1 x1, that's axial. M2 x1 is bending about x2. M3 x1 is stress resultant of moment about x3. So that's how you can evaluate stresses. So this expression essentially represents the strain measures, and we multiply it with Young's modulus to evaluate stresses. So this also assumes that there is symmetry about one of these axes, x2 or x3, in the cross section. Otherwise there would be a term of H23C. And of course these superscript C means that we are evaluating these quantities at the centroid, or the frame at the centroid of the cross section. So now couple of quick questions for you guys. There is a cross section which has layers of different materials. So it's not one isotropic material, it's many layers of isotropic materials. So each layer has E as the material property, and let's say AI as the area, again EI. So now we need to know how the strain distribution would look like. Would it be continuous across all the layers or discontinuous? Any ideas? Okay, so the strain be continuous and stress be discontinuous. Why is that?
You can't have delamination between the layers.
Okay, so assuming that this layer is bonded to the other layer with a perfect bond, then there is no delamination between the two layers. So strain, being a kinematic quantity, has to be continuous. But why is stress discontinuous? Or why it can be discontinuous?
Because it depends on the material.
It depends on the material. So there is multiplication of strain with material property, and if there is a difference or significant difference in material properties, you'll see a jump in stresses. So while the strain, let's say for a beam like this, whose cross section is here, this would be the initial, if there is a moment, this would be the initial phase of the beam, and finally the strain may look like something like this if there is a moment on the beam, right? But the stress distribution could be something like so there can be discontinuities, there can be jumps in the stresses, right? So that's something important to note. Now let's do an example. So there is a cantilever beam. So cantilever beam fixed at the root. Let's define a coordinate frame of reference. let's say we have x1 along the length or the span of the beam, x2 going vertically upwards in the cross section, and x3 going towards the left. Let's say the length of the beam is L, so the span is L, the width of the cross section is B, and the height of the cross section is H. And the modulus E. So it's a rectangular beam. Is there any plane of symmetry? Is there a plane of symmetry? Okay. So this expression holds. Now, where would be the maximum stresses? At the fixed end? Is there any load applied? Well, let's neglect the weight of the beam. So where would the maximum stresses be?
What are the loads?
So there are no loads. So no loads means no stress, means no location for maximum stress. So let's give this beam a loading. We have P1, which is an axial load coming out of the beam, applied at the centroid, and a transverse shear force, P2. I'm just trying to be consistent with the notations or the coordinate frame. Okay, so we know that H23C is going to be 0 because there is a plane of symmetry. And we know that we are evaluating everything at the centroid. So if you want to just represent this problem in a beam, like a 1D beam reference line form, essentially there is an axial load P1 at the tip, and there is a transverse shear force P2. Okay, some of the sign conventions. So if the axial load essentially is applying a tensile force on any given body, then we consider this as positive. If there are moments and shear forces applied on a body such that it's vertically upwards on the right end for V2, and moments are applied in an anti-clockwise manner at the right end, it's positive. But so this would be positive. So these are three different deformation modes. This is axial, this is moment about x3, this is moment about x2. So these are the sign conventions that we would be following throughout this course. So let's evaluate. Let's evaluate where the stresses are, where are the maximum stresses, and whatever we need to know from this problem. So first of all, we would need to evaluate N1x1, M2x1, and M3x1, so that we can substitute these values in this expression. We would also need to evaluate H33 and H22 and S. So let's say we make a cut, somewhere in the beam at a distance of x1 from the root. So essentially we are cutting this beam. So what do we have? We have a free body diagram where P1 is applied, and we have a N1 x1 as the stress resultant. So N1 x1 would be P1. Right? Now let's look at, so we have only P2, we do not have P3. So there would not be any moment about x2. There would only be a moment about x3. So we have another free body here where P2 is applied at the right end. Then we have V2 x1 as the shear force at the cut. We also have a moment M3 x1. So taking the positive sign conventions from here, and we will take the moments and sum them equal to 0 at this point. So what do we get? We get M3 x1 minus M3 x1 because it's clockwise, plus P2 L minus x1 is equal to 0. Correct? So we evaluate M3 x1 as P2 times L minus x1, and we know that M2 x1 is equal to 0 because there is no load. So if M2 x1 is 0, this term in this expression for the stresses goes to 0. We are left with the first and the third term. Any questions about this? So we are calculating moment about this point, and this is the portion which was cut out from this beam. So what's the lever arm for this force? It's L minus x1. Okay. So now let's evaluate the sectional constants S and H33C. We do not need to evaluate H22C because that term is 0. So S we know is equal to integration over the area, E dA. So E here is uniform, so we can take that out of the integral. So it becomes E integration of 1 dx2 dx3. So it becomes, and the limits here will be minus b by 2 to b by 2 for x3, and minus h by 2 to h by 2 for x2. So this essentially becomes E times B times H, which is E times the area of the cross section, actual stiffness. Let's evaluate H33C. It will be integration of the area E times x2 square dA. It will become just splitting the integration of the area in two components. So this becomes E times integration from minus b over 2 to b over 2 times x2 cube over 3 limit minus h over 2 to h over 2 times dx3. So this becomes E times b times h cube over 12. Any questions? Okay, so let's take this stress expression for the stresses at any point in the beam and substitute all these values. So we get sigma 1 x1 comma x2 comma x3 is equal to E times P1 over E B H minus x2 P2 L minus x1 over E B H cube over 12. So I'm just multiplying that on the other side. You can cancel the E. So we are left with P1 over BH minus P2 L minus x1 over BH cube. So it's important to note that the stresses here do not depend on E, the material property. And that's the case only with a cross section or a beam which has a uniform material property. If there was a layered composite section or layered beam section, then the modulus will not cancel out. Can everyone see this? Yes, go ahead. I think I missed a 12. Thanks. Yeah, there's an x2. Okay. So we evaluated an expression for stresses. Where will that expression be maximum? What should be the value of x3 for that expression to be maximum? We need to look at all x1, x2, x3, right? We have a 3D problem. So we have to look at the locations where the stresses are maximum. So what should be the value of x3? x3 can take any value, right? Because it's not in the expression. So x3 literally can take any value over the domain. what should be the value of x1? Can be any value. This term has to grow, right? And x1 is negative. If it's L, that term will become 0. It has to be 0, which was the answer given by her in the first time. So x1 has to be 0 so that the stresses are maximum at the root, but we have not identified a location yet. We have identified that all the values of x3 and x1 0 stresses will be maximum, but we are missing information about x2. So what should be x2? We have maximized this term, but there is a negative sign here, right? So x2 will be minus h over 2, because that's the most negative value in the whole cross section, right? So x2 is negative of h over 2. x2 is minus h over 2. x3 can take any value, and x1 is 0. That's this line. So the stresses will be maximum at the lower end of the root, or the edge, the lower edge of the root. What would happen if there was no P1? There was no axial load. So if there is no axial load, this term would go to 0, right? So if there is no P1, there is no axial load, then what will happen? That term goes to 0. Now when we try to calculate the maximum stresses, we now have two locations, one on the top edge and one on the bottom edge. Any questions there? So we will just try to maximize this term then, and when we maximize this term, it is maximized at both h over 2 and minus h over 2 for x2, right? One would be a positive stress, one would be a negative stress, but they both would be maximum. So there would be two locations, two edges for maximum stresses, but because there is an axial stress, there is no longer a maximum stress on the top edge, it's only at the bottom edge. So now that we have the locations for x1, x2 and x3, we can evaluate the sigma 1 max. So you can essentially replace x1, x2, x3 with 0, comma, minus h over 2, comma, x3, and it will become P1 over BH minus 12 P2 L over BH cube times h over 2, right? So this goes away, P1 over BH plus 12 P2 L over BH square. Okay, another important observation here. At the root, now that the maximal stresses came at the root, and there are tensile stresses at the root and there are compressive stresses at the root. Tensile stresses are positive in nature, compressive stresses are negative in nature. So there should be some location where the stresses are 0, right? Why it's important to find out where the stresses are 0? Because we do not need material there. If the stresses are 0, the beam doesn't need to support any loads there, so we can take off the material from there, right? So it's in engineering design, it's an important consideration. So let's find out where the stresses are 0. So what happens? P1 over BH minus 12 P2 L minus x1 over BH cube times x2 is equal to 0. We are looking at the root, so x1 goes to 0. So we can simplify some things. So this becomes x2 is equal to P1H square over 12 P2 L. Of course, if there was an x1, then you can put value of x1 and evaluate that location of 0 stress at all the cross sections along the span. But we are just looking at the root. So what value can x3 take? Any value. x2 is this. It's a positive value. So it means if I have this as my cross section, and my centroid is here, I have x1, x2 and x3. Then there is some there is a line which exists at some distance x2 prime, which we evaluated there, where the stresses are 0. So we call this as neutral axis. It's an axis in the cross-sectional reference frame where the stresses are 0. What would happen if the axial loads were not there? What would happen to this neutral axis if the axial forces were not there? Yeah.
Neutral axis would be on the axis of symmetry,
On the x3. So neutral axis would be parallel to x3 and it would be passing through the centroid. Can neutral axis go outside the cross section? It can go outside the cross section. If the axial loads are too high, this line would keep moving further away. So this axis will no longer be in the section. Okay. So this ends our example. I hope it was helpful. Okay, so far we evaluated our sectional constants h22, h33 at the centroid, assuming there is a symmetry in the cross section. But oftentimes there is no symmetry and we do not evaluate them at the centroid, right? So how do we calculate these quantities, or how translation or rotation of coordinate frames affect these quantities? That's what we are going to study, because not only that will help us know what are the behavior of those sectional constants, it will also help us identify how the behavior of the beam, neutral axis, the location of maximum stresses change with the change in the cross sectional coordinates, right? So let's assume that we have an arbitrary body with origin placed at O. The axes are x2 and x3. These are only cross sectional axes. We are talking about cross section, so we are not dealing with x1 right now. And let's say that our centroidal frame of reference lies somewhere here and is parallel to the frame of reference, which is situated at O. So we know that h22, h33, h23, these are the quantities associated with the frame of reference, which is governed by x2 and x3. And then we have quantities h22 prime, h33 prime, h23 prime. These are associated with the centroidal frame of reference, which is x2 prime and x3 prime, right? So these properties, they are dependent on geometry, then it depends on the material property, and its distribution, and it depends on the choice of reference frame. Any questions about any of these? Okay. So we know that h33 is integration over the area E x2 square dA, right? Now let's translate this quantity from the reference frame x2 x3 to the centroidal frame x2 prime and x3 prime. I'm calling this superscript of apostrophe as prime. So we have to first identify the coordinates, because there is an x2 here. So x2 will be represented as x2c plus x2 prime. Is it correct? Any questions?
X2C is the difference between difference between the origin and centroid
Yes.
in that axis.
So from the origin, the coordinates of the centroid are x2c and x3c. So I'm representing x2 in terms of the frame of x2 prime and x3 prime. So I'll substitute this value in that expression. So h33 becomes then just algebra. I'll separate the terms now. It becomes E x2c square dA plus integration over the area E x2 prime square dA plus 2 integration over the area E x2c x2 prime dA. Okay, so this x2c is a constant. It's a quantity which defines the centroidal location of the centroid in the reference frame attached to O. So this just becomes x2c integration over the area E dA plus integration over the area E x2 prime square dA plus, again, x2c is a constant, so I'm taking that out, x2c integration over the area E x2 prime dA. Okay, so we are moving to a centroidal reference frame, right? So what happens with this integration? Zero, because it becomes an odd function. What is this integral? Integration A over the area E dA. It is S. What will this become? H33 prime. So in a centroidal, yes, go ahead.
Should there be a squared on the x2c on the first integral?
Correct. Apologies. So we have now related the sectional constant H33 with its counterpart in a translated frame of reference, where the translated frame of reference is a centroidal frame, right? So we can say that H33 is equal to H33 prime plus S times x2c square. H22 is equal to H22 prime plus Sx3c square. This is sometimes referred to as parallel axis theorem. A lot of times it happens in a problem that you cannot evaluate, or you may not want to evaluate H22 or H33 about the origin. You may want to evaluate at the centroid of that particular portion, and then you may want to translate it and add it. So that's why this theorem is helpful, but it's important to note that the additional term went to 0 only because we have a centroidal frame of reference. If we are not dealing with centroidal frame of reference, this term will not be 0 and needs to be accounted for. So we looked at the translation here. Now let's look at the rotation of axis. So let's say I have an arbitrary body with origin O and a coordinate frame x2, x3, sectional coordinate frame x2, x3 attached to O, and I'm rotating this coordinate frame by a positive anti-clockwise angle alpha. Okay, so I had h22 star or prime is equal to integration over the area e x3 prime square dA. Now after rotation of coordinates or coordinate frame in this case, my x3 becomes x3 times cosine of alpha minus x2 sine of alpha. So I'll substitute this expression. Okay, so I'll expand that expression. So h22 prime integration e becomes x3 square cosine square of alpha plus x2 square sine square of alpha minus 2 x2 x3 cosine of alpha sine of alpha dA. So now I have, just simplifying this expression, cosine square alpha is a constant because alpha is a constant. So I'm taking this out of the integration. Similarly, I'm taking sine square alpha out of the integration. And then I'm taking 2 cosine alpha sine alpha out of the integration. Good management of space. Okay. So what's this term over here? H22. This term becomes H33 and this terms become H23. So again, we represented sectional constant H22 for the rotated section or rotated frame in terms of the sectional constants of the original frame. If you do a similar operation on H23 and H33, you'll be able to obtain some expressions which I'll directly write. So H33 will become H22 sine square alpha plus H33 cosine square alpha minus or plus 2H23 cosine alpha sine alpha. And H23 prime can be written as 1 over 2 H22 minus H33 sine 2 alpha plus H23 cosine 2 alpha. Okay, so when we had symmetry in the cross section, H23 used to go to 0, and that was one of the annoying non-diagonal terms in the matrix anyway. So if we want to simplify our equations, we would like to find locations where H23 prime goes to 0, right? Because it may happen in an arbitrary cross section like that H23 doesn't go to 0. So is there any other possibility where H23 prime can go to 0? So we can evaluate alpha for that. So what we essentially do is assign H23 prime equal to 0. It means 1 over 2 H22 minus H33 sine 2 alpha plus H23 cosine 2 alpha goes to 0. So it means H23 cosine 2 alpha is equal to H33 minus H22 over 2 sine 2 alpha. So it means that tangent of 2 alpha, which is sine 2 alpha over cosine 2 alpha, is equal to H23 over H33 minus H22. So we can evaluate alpha from here. Any questions? Okay, so this is called as, so or the axis represented by alpha is known as principal axis of bending, and we will discuss about this in the next class. Any questions? You've got 1 minute.